We're a 27-year-old company focused in IT, machine learning, geospatial systems, and process automation. I'm leading the machine learning practice in the company. We started, a bit ago. I've got about 15 years of machine learning experience, and we started this effort within the company. And this is one of the prototypes that we've developed, and I'm pleased to be able to share that, what we've been able to do with you today. So if you go to slide 2. Hold on, I'm having a technical issue. There we go. So what I'm going to do is I'm going to just describe to you the technical challenge that we were addressing with this, where the data came from, what the actual challenge was, talking about the data that we were provided, how we analyzed that data and developed features for the machine learning solutions, then how we designed that solution. Give you a quick overview of some unsupervised learning techniques. Those are not quite as common as the supervised learning that people are probably more familiar with. Then how we implemented it, and then the results of of what we were able to do to detect cyber events within this industrial control system. We go to slide 3. This is the diagram on the right just shows you an overview of the water distribution system that this data represents. Our goal is to detect cyber attacks onto this system. So we're going to be provided data that it indicates how the system is operating, and then the system will be attacked by outside, and our goal is to detect when those attacks occur. And then through this, we're going to illustrate the machine learning techniques and design processes that we used to solve this challenge. Slide 4, please. So the data source came from a group that they sponsor these challenges, the Battle of the Attack Detection Algorithms. You can download the data set yourself there if you're interested. But it's based, like I mentioned, on a cyber attack on a water distribution system. They provided us with 3 data sets. So the first data set was the system in normal operation. And then they provided a training data set, which contained data of the system that was under attack. And then the final one was what we kind of held aside as a test data set. So we did not do any training on it, but it was when the system was also under attack. You go to slide 5. I've got a sample of the data that we were provided. So you can see the data provides information such as the level of the tank, the pump switches, pump flow rates, valve positions, valve flow rates, and then pressures at a wide variety of sensors. Each time instance, and the times were separated by an hour. Each time instance, they gave us 43 features to look at. Going on to slide 6. So I mentioned that there were 2 data sets where there were attacks. In the first one, which we're going to call the training data set, there were 7 attacks, and they were of a variety of different types of attacks that you might see against an industrial control system of this nature. There was a replay attack, and then there were some where they were adjusting, altering the tank level readings, some where they were reducing pump speeds. Those are the nature of the attacks that they were conducting on this water distribution system. The orange line, when it goes up, indicates each of the attacks, and you'll see this type of representation used a little later on. The second, if you go to slide 7, this is the attacks that were really that are going to be in our test data set. And so our goal is really we're never going to use this test data set in training. We're only going to use this to test the final outcome of our solution. So we'll use this as our primary measure of how effective our machine learning solution is in detecting these cyber attacks. If we go on to slide 8, so we began by taking a look, at all the different data features. One of the things I'll note is that they did not provide a change in level of the tank from data point to data point. We actually created that feature ourselves. That's the DL_T1 through T7 that you see at the bottom of the chart. We felt like that was the amount the tank changed over a period is also interesting information that we wanted to provide directly to our solution. In here you can see that the red features, and particularly the darker the red it is, it means that they're positively correlated. Blue features are negatively correlated. And so we see some, you can start to see some interesting features of the data, some not necessarily so interesting, but you can see that the flow in a pump is non-surprisingly directly related to the switch position. They're very highly positively correlated, which is what you would expect. But we saw some other correlations. In some machine learning instances, highly correlated data might not be desired, and you might want to remove some of the data or perform some dimension reduction techniques to reduce the correlated data sets. We felt like, because of the nature of this problem, which is going to be identifying anomalies in the way a system is performing, that keeping the correlations was probably a good thing. So we did not remove or reduce the correlated data. We feel like that the breaking of a correlation might indeed indicate anomalous behavior, and you might be an important feature for us to identify an attack. So we did leave those correlated features in. A couple other items to note: pump 1 is used 100% of the time in the normal operation data set. Pumps 3, 5, and 9 are never used. And then one which we'll cover in a little bit in the next slide is pumps 6 and 11. They are only very rarely used. And we'll talk a little bit more about this. If you go on to slide 9. So when you have a case where something is only rarely used, you have to be careful, because this can show up as an anomaly in your data. Also, since we're going to normalize the data, meaning that we're gonna take our data set and we're gonna force the data to a 0 mean and a 1 standard deviation. What happens in a case like this, and you can see in the chart at the bottom of this graph, is you end up with a very small standard deviation. So the thick red lines you can see around maybe 0.02. That's the standard deviation. And so if you normalize this data, you'll end up with a very, very large value because it is only switched on occasionally. This causes some challenges. You can't just normalize the data and forget about it. You need to take some actions. One is that you can limit how high you'll allow your normalized data to go. We often use 3 standard deviations, because data beyond that is certainly going to be an outlier. The other option you can do is to not normalize this particular feature. In our case, we did decide to just limit the size of that feature to 3. So if we go on to slide 10, we're going to talk a little bit about the solution architecture. So what we knew going in is that we had a data set with no attacks that was provided. It's not terribly large. I think it was 8,000 some odd time slices, which is not very large for a machine learning project. There was also limited data with attacks that was provided. Like I said, we're only going to use the training set of attacks, and I think that was around 4,000 time sequences, and only 7 different types of attacks. So one of the things we knew going in is that the amount of data and the variation on the attacks is going to be fairly limited, which can pose a challenge when designing a machine learning solution. Typically, you'd like a lot more data, and you'd like a lot more different types of attacks and how they would affect the system. Because we had very little attack information, we elected not to use a supervised learning technique. We felt like an unsupervised approach was going to be better. The primary difference between a supervised approach and an unsupervised approach, if we had a data set where there was a lot of attack information, we could have trained it to recognize very specifically those attacks. But because we had so few attacks, we felt like that wouldn't yield a solution. Instead, we just wanted to characterize the normal system behavior, and then it would detect anomalies in how that system is behaving in a normal environment. We investigated two unsupervised approaches. One was clustering, and the next was a neural network autoencoder. I'll give you a brief overview of each of those here in the next two slides. You go to slide, actually the next three slides. So I talked a little bit about unsupervised learning approaches. These type of approaches are useful when you have unlabeled data sets. And what an unlabeled data set is a data set where you might not, for example, in ours, we're not going to tell it, okay, here's an attack and here is not an attack. If you had a lot of that data, then you could use a supervised approach. We're going to only use the unsupervised data, at least in the first phase of this. Like I mentioned, the common approaches are clustering, and we'll talk about neural network autoencoders, which was the type of system that we ended up using. So if you go to the next slide, so we'll talk a little bit about clustering here. I'm sorry, you should be on slide 11. So slide 11, you're looking at some simple two-dimensional data, and it's been divided into two clusters. So the goal of an algorithm would be to look at these data points and determine, okay, here's cluster 1, here's cluster 2, and then to potentially identify where anomalies or data outliers are, because those are going to indicate something that's occurring in your system that's not normal. Your system it's an unusual behavior. In our case, we're looking to detect the cyber attacks as those anomalies, but they could also occur, if you had equipment malfunctions. This can also be used to detect equipment malfunctions and whatnot. So if you go to slide 12, I'm going to describe to you quickly what a neural network autoencoder is. This is in terms of neural networks, it's one of the common mechanisms used to do unsupervised learning. Because we don't have a labeled output, normally in a neural network you would train the network by feeding it an input with a matched output, and you would propagate that error back through the network, and eventually the network would learn to replicate the desired output. But since we don't have that output because it's unsupervised, what we end up doing is we feed the network an input, and we feed it when we're trying to train it to produce that same input as its output, which seems like it might be a pretty simple task. But what we force it to do is we force it to go through what you might call like an hourglass shape. So we force it to reduce the network down. And in this example, you can see it reduces the network down. You have 4 inputs, and it reduces it down through 2, and then it has to produce 4 outputs. What's important there is it's going to focus on key pieces of information that is in your data, so that it's able to replicate the output as closely as possible. So it's going to learn how to characterize your data and reproduce it on the output. It'll learn to ignore features that are not terribly important, and combine features together. And that's what that middle layer, which we call the compression layer, is doing. Designing this network, so understanding how many neurons are in each of those layers, that's really where the art form comes in designing these type of solutions, and figuring out how many neurons are in that compression layer is important in how this system is able to perform, so that it's able to detect anomalies when anomalies occur, and reject false positives. Next, please. So, like I mentioned, we selected the neural network autoencoder as the best solution for this particular problem. We refined the architecture. So once we selected that, we then started experimenting with how many layers are in the network, how many neurons are in each layer, and then most importantly, how many neurons are in the compression layer. and measuring its performance throughout. If you go to slide 14, this is the final architecture that we came upon. So you'll see on the upper right, we had 50 input features like we mentioned earlier on. We then reduced that down through 25 nodes. Then finally in the compression layer, we had 18 nodes. Then back out through 25, and finally producing the 50 features. And the goal then is that the output features of this network are the same as what's input. And as long as it can recreate that output from the input, then the system will be operating normally. Those are inputs that it's able to understand. When the output no longer matches the input within a sufficient accuracy, that's when you have system performance that's anomalous. It's not operating as we had expected it to operate. So we developed off of the normal operation data set. So that first data set we looked at, we divided that into a training data set and a test data set, and we trained this network for 1,000 epochs, which is a complete pass through all the data. And measured its performance. If you go to slide 15, this is a typical way to look at neural network accuracy. So here it's trying to model normal system performance, and you can see it's able to do that quite quickly and very effectively. It reduces the mean squared error of what the output is versus what the input is. To a very low amount. So we were very satisfied with the result, the initial result of this. And I do note here that we were able to do this actually without a significant hardware investment. I just did this on my business class laptop, and it took less than 2 minutes to train the network. Neural network problems with large data sets, that wouldn't be possible, but for this one it was something we could approach. So slide 16 show the initial results of the anomaly detection, in this case caused by cybersecurity incidents. If you recall from the earlier slide, the orange line represents the attacks. This is on the final test data set, so it's never seen this data before. And you can see just visually, it looks like it's doing a decent job detecting the cyber attacks. Values where the blue line is high indicate where there's a high error and there's an anomaly between in the input data. A couple of things that we didn't like about this. One, so the ones like attacks 3 and 4, you can see do a very good job. They match the orange lines very well, so it clearly is identifying the beginning and the end of the attack. That does a very, very good job in detecting it. If everything looked like that, we would have been done here at this point. But then if you look at the first attack, you can see how it is going up and down quite a bit. It oscillates, and it is clearly at times detecting there's attacks, and then in times it doesn't know that there's an attack going on. Additionally, over at time around 1500, you can see a false positive where it thinks there's an attack going on when in reality there's not. This turns out to actually be a very, very tough problem to solve. It's caused by one of those pumps that rarely comes on, and it's showing up as an anomalous event. So we looked at this and we said, well, we'd like to improve this result. Overall it's not bad, but we really wanted to do a better job in saying, okay, there's an attack going on during this time. So we looked at some areas for improvement, including data pre-processing, some additional pre-processing that we could possibly do on the data. But then what we ended up with was adding a second supervised neural network as a post-processor for this data. So if you go to slide 17, what we did is you can see to the left, you have the neural network autoencoder, and on the right-hand side, we added a neural network classifier. So it took as its input those 50 outputs or the error generated, I'm sorry, it took the error generated each of those outputs as its input, and then it was designed to produce a binary output. So a 0 indicated normal operation and a 1 indicated anomalous operation. We used the second data set, which included attacks, to train this network. So we didn't have a lot of data, and we didn't have, and I think in the end, we didn't have sufficient examples to train it as well as we'd like. But if you go to slide 18, you'll see the results of this. And now you can see it's doing a much better job. In the first attack, it recognizes the attack immediately. It stays in an attack state, and then it returns back to a normal state as soon as the attack ends. There's only a couple of instances during an attack where it seems to not understand that it's under attack, and also that false positive at time 1500 remains. That turns out to be a really tough challenge and that's a feature of not having enough training data. We'd really like to have more data where those pumps that rarely come on are on, so the system can learn that, okay, that is a normal situation. Right now, it looks at pretty much any time that pump comes on that it's an unusual situation. So go to slide 19. The conclusion of this is that we were able to successfully detect performance anomalies in an industrial control system. These anomalies were brought about by cybersecurity incidents. This would also work if you had mechanical failure or electrical failure in the system. It would also detect those type of anomalies. We were very pleased we were able to get these kind of results using a relatively small training data set. The accuracy was very high and was able to reject most of the false positives. We just had that one remaining. We're planning to continue this research. Really want to improve the ability to reject those false positives. The other thing we want to do is be able to identify the specific equipment that's being targeted in an attack. So if you recall from the description of the data set, we know the various components of the system that are being attacked. We'd like the system to be able to give us an indication of which of, what it thinks the components are that are being affected by the cyber attack. That would also come into play if you were looking for a machinery maintenance piece. If it's a machinery failure, you'd really like it to be able to tell you that it's okay, pump 6 has failed. So that's really where we're looking to go with this next. I think with that, I'm open to any questions that anyone might have.
Great, thanks, Scott. Appreciate that. Seems like everyone was able to hang in, and the DCS connection held for us a bit. So yeah, if there are any other questions, please, folks, for those who can hear me and are able to type them up in the window, go ahead and submit them on the chat, and I'll fill them over to Scott. Right now, there's none that have come through, Scott. The only comments in there are just from myself, pointing folks to the chat window to enter them, and then John Reed from representing DSIAC and CSIAC just bringing some links and providing some links so that the folks who do want to submit a technical inquiry through those sites have the source for that. All right, if there's any other questions, please go ahead and submit them. I will say there might be a bit of an issue with the way DCS is working right now. I think for some folks, they weren't able to get in after we started it, so I don't know if that's causing any issues with folks earshot right now.
I hope I hit the right level of technical content. Hopefully that was able to at least people could understand what we were saying and what the direction we're trying to go.
Yeah, and I appreciate that. So what we'll do too, in case I didn't already mention this before, we've been recording the presentation, and so we'll make sure we process this and make it available. We'll be putting it on our Techipedia page so that folks can access that. Same thing with the slides. The question was asked here about when the slides would be available. We will put them on our Techipedia page for download as well. If anyone wants to get them directly from Scott, they can do so, but we'll be putting them to be more publicly available, if you will, through our Techopedia page, and we'll provide a link for that in a follow-up email that everyone should be getting within the next few days or so. But then, Scott, so question here says, are there any planned ideas on dealing with the false positives in future work?
Yes. No, that's really the biggest area that we want to research. So we believe that one of the key reasons that we have the false positives is because of a lack of data. So we think that having more data around those would help. So we've looked at some data augmentation techniques. So essentially increasing the amount of points with those data in it. We're also, obviously if we could get, more data where that pump was actually running in real circumstances, that would help. If neither of those two works, we want to look at some other techniques to improve that. We're going to continue experimenting with that, with the layer at the end, to see if we can use it to detect a false positive. So that is probably the number one thing we're trying to solve right now, because it is a condition that's normal. It did have some data to indicate that was a normal condition. So we are working to see what we can do to resolve that.
Good. Yeah, that's a great question. The only other question right now is just another interest in the slides. And yes, again, I'll make sure we make those available. They'll be on our Techopedia page, but more importantly, we'll email out a link to everybody for where they can get those. And then I'm sitting on the last slide in the presentation, so for those who can see that, there's an email and phone number there for Scott if you did want to direct any questions to him directly. Otherwise, of course, the technical inquiry service is open for anybody to submit them through DSHD or CSIAC. The question here,
something else.
Go ahead.
If anyone has any feedback for me, if there was something that could be done to make the presentation better, I'd also appreciate any feedback. So if you have some comments, I'd feel free to drop me a line. I'd be interested in hearing that, so we can improve this for the future.
Well, one question for clarification was, what type of autoencoder was used?
So it was a neural network autoencoder. I'm not sure what other information might be asked for there, but essentially it's a specific architecture of neural networks. The key features being that it reduces the number of inputs down through that compression layer, and it is trained by trying to replicate the input on the output. That's kind of the key feature of that neural network autoencoder. If that does not answer the question, please let me know.
Yeah, well, the clarification I just typed in here was variational or sparse, perhaps something else.
I'm not familiar with that, so I don't know how to answer that question.
Okay. I suppose the implication there is that autoencoders would be qualified as being either variational or sparse or something of that sort.
Yeah.
Okay. Well, if there's no other questions, we can kind of go ahead and close this out. Wait, pause for another second or two to see if any come through. Okay, well, Scott, I very much appreciate you taking the time, delivering the presentation. Thank you for the content and all that you presented. I think it was very well presented. So if I have any other feedback, I'll be sure to let you know. But otherwise,
okay,
we'll make this available for folks. And again, if they want to get in contact with you, your number and email are all on these slides, so they can get in touch with you that way. And the slides will also be available. So, Scott, thank you very much.
Okay, fantastic. Thank you very much.
All right, thank you everybody for attending.
All right.